Welcome to Agentic AI World, your daily interview prep for senior AI engineering roles. I'm your host, and today is episode 37. Today's topic, AI Federated Learning, how senior engineers build privacy-preserving machine learning systems at scale. If you're interviewing at a top-tier AI company, expect questions on federated learning the moment privacy or edge deployment comes up. Let's break it down the way a senior engineer would. What is federated learning? Federated learning is a machine learning approach where the model trains across many decentralized devices or servers, each holding local data, without ever moving that data to a central location. The key insight: instead of bringing data to the model, you bring the model to the data. Each client trains on its local dataset, computes gradient updates, and sends only those updates, not the raw data, to a central server. The server aggregates them and sends back an improved global model. Classic use cases include mobile keyboards, think Gboard, healthcare systems where hospitals can't share patient records, and financial fraud detection where banks can't pool transaction data. The architecture: what you need to know. A production federated learning system has 3 layers. First, the client layer. Each client, a phone, hospital server, or edge device, trains a local copy of the model. It computes gradients using its private data and sends compressed gradient updates upstream. Second, the aggregation server. This is the coordinator. It receives updates from thousands of clients, aggregates them, typically using FedAvg, federated averaging, and produces a new global model. The aggregation server never sees raw data. Third, the communication layer. This is where most production problems lie. Bandwidth is expensive. Clients go offline. Updates arrive out of order. You need compression, quantization, and robust retry logic. FedAvg, the core algorithm. The interviewer will almost certainly ask you to explain FedAvg. Here's how it works. The server sends the current global model weights to selected clients. Each client runs stochastic gradient descent on its local data for a few rounds, producing updated weights. Clients send their updated weights back. The server averages them, weighted by the number of samples each client trained on, and that becomes the new global model. The formula: global weights equals sum of client samples divided by total samples times client weights. It's elegantly simple, but production is messy. The hard problems in production federated learning. Non-IID data. Client data is not independently and identically distributed. A keyboard user in Tokyo types differently from one in Lagos. A hospital in a rural area sees different patient demographics than an urban center. This data heterogeneity causes model drift. Senior engineers solve this with techniques like FedProx, which adds a proximal term to the local objective to prevent clients from straying too far from the global model. Communication bottlenecks. With millions of clients, even small gradient updates become a bandwidth problem. Solutions include gradient compression, quantization down to 8-bit or even 1-bit, and sparse updates, only sending the top K gradient values. Differential privacy also adds noise, which further reduces the useful signal, so you're constantly balancing privacy versus accuracy. Client dropouts and stragglers. Not every client finishes training in time. You need asynchronous aggregation strategies and mechanisms to handle partial updates gracefully. Production systems set a minimum participation threshold. For example, only aggregate when at least 60% of selected clients respond. Privacy attacks. Sending gradients is not the same as sending raw data, but it's not perfectly private either. Gradient inversion attacks can reconstruct training samples from gradient updates. The defense is differential privacy, adding calibrated Gaussian or Laplace noise to gradients before sending. The privacy budget, epsilon, controls the trade-off. Lower epsilon means more noise, more privacy, less accuracy. Secure aggregation. One advanced topic that impresses interviewers: secure aggregation. The idea is that clients encrypt their gradient updates using cryptographic masks. The server can compute the sum of all updates for aggregation without ever seeing any individual update in plaintext. This is important because even the aggregation server shouldn't be trusted with raw gradients. Secure aggregation, combined with differential privacy, gives you a strong privacy guarantee end-to-end. When to use federated learning versus centralized training. Interviewers love this comparison. Here's your framework. Use federated learning when data cannot leave the source due to regulation, HIPAA, GDPR, data volume makes central storage impractical, or low latency on-device inference is required. Use centralized training when you need maximum model accuracy, you have control over data collection, or the computational overhead of federation isn't justified. The honest answer is that federated learning trades accuracy and engineering complexity for privacy and data locality. You need to be explicit about that trade-off. System design, federated learning at scale. Here's how you design a production system for, say, a global mobile keyboard. Client selection. Randomly sample a fraction of available clients each round, typically 1 to 10%. Prefer clients on Wi-Fi with sufficient battery. Local training. Each client trains for 5 to 10 local epochs with a small learning rate, then compresses and quantizes gradients before transmission. Aggregation. The server uses FedAvg with differential privacy, clipping individual updates to a max norm and adding Gaussian noise before averaging. Model versioning. The server maintains versioned global models. Clients report which version they trained against, and stale updates are downweighted or discarded. Evaluation. Since you can't centralize test data, you evaluate on a held-out proxy dataset at the server plus federated evaluation rounds where clients report local metrics. Infrastructure. Google's TensorFlow Federated, Meta's FLSIM, and NVIDIA Flare are production frameworks worth knowing. PySYFT from OpenMind is popular for research. The interview framing. When a senior engineer talks about federated learning in an interview, they're not just describing the algorithm. They're demonstrating systems thinking. Show the interviewer you understand the trade-offs: accuracy versus privacy, communication cost versus update frequency, system complexity versus regulatory necessity.